In this problem, we have an inner sphere with charge Q, and we have outer spherical shell with no charge on it. And the inner sphere has radius A, and the inner spherical shell has radius B, and outer spherical shell has radius C. And these two materials are both metallic, which means that they are good conductors, and on a good conductor, all the charges are free to move around. The first part of the problem is asking us, what's the charge going to be in the inner spherical shell as well as the outer spherical shell? Okay. And if the charges are free to move around, then all the negative charges will be induced in the inner surface, because these are the charges that will be attracted to the positive charge inside of the positive charge on the small sphere. Yeah. And because we started off with a zero net charge, there has to be some positive charge that counters the induced negative charge due to conservation of charge. So all the positive charge will be on the outer spherical shell, and all the negative charge will be induced in the inner spherical shell. Okay, so inner spherical shell, we have charge minus Q, and outer spherical shell, we have charge positive Q. And the second part of the problem is asking us, what is the electric field at various locations? Okay? And the expression for electric field is given by integral of electric field at some surface element is equal to the enclosed charge divided by the permittivity constant. And since we have a spherical symmetry, the electric field is going to be constant throughout a spherical shell that is extended by some radius. So therefore, this expression will simply reduce to electric field times the surface area of some sphere by radius r. So that's 4 pi r squared enclosed charge divided by epsilon naught. And therefore, the electric field is Q enclosed divided by 4 pi epsilon naught r squared. So this is the equation with which we solve what the electric field is. And the first part is asking us what the electric field is inside of this sphere. Just like the negative charges moved to the inner sphere, inner spherical shell, all the positive charges will move to the surface of the sphere, because they'll be attracted to this minus charges. So all the positive Q is on the surface of the sphere, so therefore inside of the sphere there's no charge. So the enclosed charge is 0, so therefore the electric field has to be 0. So for R less than A, electric field is 0. Okay. And the second part is asking us what the electric field is between A and B, so in this region. Okay. So in this region, we see that the enclosed charge is plus Q. So therefore, the electric field is equal to Q over 4 pi epsilon naught r squared, and this is between A and B. Okay. And the third part is asking us what the electric field is between the spherical shell. And we can see that in this region, the enclosed charge is plus Q and minus Q. So therefore, again, the net charge is 0. So between B and C, electric field is 0. Okay. And the last part is asking us what the electric field is beyond C. So R greater than C. And we can see that the electric field, the total enclosed charge is plus Q, minus Q, and plus Q. So therefore, total enclosed charge is Q again. Therefore, electric field is equal to Q over 4 pi epsilon naught R squared, which is the same expression as in this case. And part C is asking us to plot electric field as a function of the radius. Okay, so electric field as a function of radius. And we can see that the behavior is different for different regions. So for instance, between 0 and A, electric field is 0, whereas between A and B, the electric field is just decreasing with R squared behavior. And between B and C, the electric field is again 0. And C and beyond, the electric field is again monotonically decreasing. And the last part of the problem is asking us to calculate the final velocity of an electron. Okay, so when we have an electron with, we have electron of mass me and it's carrying charge minus c, and initially it's located at infinity, and initially it has velocity of 0. Okay. And with this information, we want to calculate the final velocity of the electron when it's at distance 10c. So since we are dealing with initial velocity and final velocity, we might want to invoke conservation of energy. So initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. Okay? And we immediately know that the initial kinetic energy is 0 because initial velocity is 0. Now all we have to do is figure out what the potential energies are in order to figure out what the final kinetic energy, therefore the final velocity is. Okay? And the change in potential energy is given by the expression minus work. Okay? And work is given by the expression integral of initial distance to the final distance of the force that's acting on the electron to the distance through which this electron travels. And force for electron or any charge is given by electric field times its charge. So therefore, force in this equation will be just given by the electric field expression, okay, greater than c, since we have 10c, okay, q over 4 pi epsilon naught r squared times the electric charge, which is minus c. So this minus sign goes away. Dr. And we're integrating from initial distance, which is infinity, to the final distance, which is 10c. And all we have to do is just evaluate this integral. And when we do so, this is minus